This is Jack Creel, and I'm going to be going over my Project 2 problem solutions. So my first two problems are both about cooking a chicken breast and finding how long it'll take for the center of the chicken breast to reach a safe edible temperature of 75 degrees Celsius. So if we come down here, we'll see we're cooking them in a 180 degrees Celsius oven from 25 to that mentioned 75 degrees Celsius. The first problem is going to use lumped analysis to find the cooking time. And the second problem will find a much more accurate cooking time, actually taking into account the temperature variation with position in the chicken. So we're assuming unseasoned chicken, unfortunately, just so that the properties are the same for the whole thing, that the properties are constant with temperature, that the heat transfer coefficient is constant. The first problem, we're going to have to assume that the BO number is less than 0.1, so that lumped analysis will apply. This is obviously not accurate, as we'll see, but we're just doing this problem for comparison purposes, so that's just fine. For the second problem, we have to assume that the Fourier number is greater than 0.2 so that the one-term approximations will apply. We're going to verify that assumption. And then we go ahead and grab our properties. I found a slightly more accurate thermal conductivity for chicken than what was available in the handout. And we draw our diagram with our coordinate system, setting 0 at the center of the cylinder. And so for the first problem, lumped analysis, we have our lumped analysis equation here. We need the time constant B, which depends on these properties. Just plug and chug. Once we have our time constant, we can rearrange the equation for time, and we will find that if lumped analysis did indeed apply, it would only take about 10.5 minutes to cook this chicken breast. But we know that the thermal conductivity of the chicken is relatively low, among other things, and there will definitely be temperature variation with position. This lumped analysis definitely won't apply, and so the more accurate answer we're about to find will likely be much larger than this. So we move on to that, where we actually take into account the geometry of this chicken breast here. So the way it's modeled, we can see that the chicken can be modeled as the intersection of a plane with a cylinder. So we're going to take the product of the solutions for both cylindrical and a plane. And so we'll start with the cylinder, which has this equation. We start with the BO number, which for a cylinder depends on the radius. So plug and chug. Once we have that BO number, we can interpolate in our handouts to find the important coefficients for this equation. Once we have those two, we can go ahead and plug them into that equation, and there is our solution for this geometry. Then we can move on to the next geometry, start with the BO number again, except now we will use this characteristic length instead of the radius, which is going to be half of the total length of the cylinder based on our coordinate system here. And so once we have that BO number, we can again use it to find the important parameters for this equation. And notice this equation is slightly modified from the one for cylinder above. And so once it's plugged in, we now have the solutions for both geometries. We can take their product to get the total solution. And since we know the desired temperature at 0, 0, the center of the chicken breast, we can go ahead and rearrange this equation for tau. And once we find the value of tau, we'll see that our assumption is verified. It's greater than 0.2. And then we can go in there and actually find the time, rearrange here and find the time, and see that the more accurate cooking time should be just over 28 minutes, which is significantly larger than what we found in the first problem using lumped analysis, as we expected. So going over the learning outcomes we just tackled here, both of these problems are obviously going to be talking about both convection and conduction. So there is those learning outcomes. The first problem is lumped analysis, which is zero-dimensional. There's zero-dimensional transient heat transfer here, so that's that learning outcome. And then problem 2 will tackle both the 1 and the 2/3 dimensional transient heat transfer analysis, because we're actually taking into account the change of temperature in space here, and in more than one dimension. So that's why we get the multi-dimensional learning outcome there. And we'll also notice that since I did both cylindrical and the plane, that we have tackled both the cylindrical and Cartesian coordinates here as well. So moving on to the last problem, we're still working with the same system here, making our dinner, except now we're going to go back and try to find a more accurate heat transfer coefficient for the oven. So for part A, we will find the heat transfer coefficient for an average convection oven, and then for part B, we will find the heat transfer coefficient for a very old oven in which the air is still, so there's no convection, just natural convection is going to be happening in there. And so we'll see that is indeed the case. Part A will do external forced convection to find the heat transfer coefficient, and part B will use the natural convection to find the heat transfer coefficient. So we're assuming air is an ideal gas with constant properties. The atmospheric pressure is 1 atmosphere. Then we're going to assume the surface temperature of the chicken is going to be at a constant value of its average 50 degrees Celsius instead of changing, and that the gravity is 9.81 meters per second squared, and that the convection is cross flow to the cylinder. So we grab our properties again and draw our diagram. For part A, the external forced convection, we start with our Reynolds number, plug and chug. And once we have that, along with the Prandtl number from our handout, we can go and find the best Nusselt number equation, which is going to be for this system, will be the Churchill and Bernstein for cross flow over cylinders. So we go ahead and plug into there, find our Nusselt number. We know how the Nusselt is related to the heat transfer coefficient. So we just need to rearrange to find the heat transfer coefficient. And we'll notice it's far lower than what the internet said an average value was. So if we were to use this in the previous problem, we should know that it's now going to take our chicken much longer to cook. We'll get a much larger value for time because there's less heat transfer going on here. The heat transfer coefficient has gone down. So then for part B, we are now doing natural convection, so we'll start with the Rayleigh number instead, and we calculate that as follows. Once we have the Rayleigh number, we can go and find the most accurate Nusselt number equation again for now natural convection, which will be this one. And then we plug everything in and find our heat transfer coefficient from the Nusselt number again and see that it's gone down even more. It's a very low value now, meaning that it would take even longer to cook this chicken. So for this problem, we have now tackled, again, convection and convection, except now we have covered both natural convection in part B and the learning outcome of external forced convection in part A.